Static equilibrium is a fundamental concept in physics that describes objects in perfect balance. An object is in static equilibrium when it is both at rest, meaning no linear motion, and not rotating, meaning no angular motion. For this to happen, the net force and net moment acting on the object must both be zero. This relates directly to Newton's first law of motion, which states that an object at rest stays at rest unless acted upon by an unbalanced force. To briefly review, forces are pushes or pulls on an object, as shown in free body diagrams from the previous video. The first condition for static equilibrium is that the sum of all forces must equal zero. This is written as sigma F equals zero. This condition breaks down into components for each direction. The sum of forces in the x direction must equal zero, the sum in the y direction must equal zero, and for three-dimensional problems, the sum in the z direction must also equal zero. This means forces in each direction must balance out. Let's look at a simple example. A block resting on a table. The weight of the block pulls it downward, while the normal force from the table pushes upward with equal magnitude. In this case, the forces are balanced. The downward weight equals the upward normal force, so the net force is zero and the block remains at rest. The second condition for static equilibrium is that the sum of all moments or torques acting on the object must equal zero. This ensures no rotational motion occurs. Torque, also called moment, is the tendency of a force to cause rotation about a pivot point or axis. It depends on both the force applied and the distance from the pivot point. The magnitude of torque can be calculated using either the cross product of the position vector and force vector, or by multiplying the perpendicular distance by the force component. The pivot point, or axis of rotation, can be chosen anywhere on the object. Different choices may make the calculations easier by eliminating unknown forces. For sign convention, counterclockwise moments are typically considered positive, while clockwise moments are negative. The important thing is to maintain consistency throughout your calculations. Free body diagrams are essential for analyzing static equilibrium problems. They isolate an object and show all forces acting on it, providing a clear visual foundation for applying the equilibrium equations. Consider a box resting on a surface. We'll build its free body diagram step by step. First, the weight force acts downward due to gravity. We represent it with a downward arrow and label it clearly. The normal force acts upward perpendicular to the surface. As a reaction force, we color it green and label it accordingly. An applied force, like a push, is shown in red with the correct direction and labeling. Friction opposes motion, so it's shown in the opposite direction to the applied force and colored green as a reaction force. Tension in a string pulls away from the object and is also colored green as a reaction force. When choosing a coordinate system, place the origin at the object's center. Label the axes clearly with positive directions. Remember, accurate free body diagrams with clear labeling, proper directions, and a well-chosen coordinate system form the basis for all static equilibrium solutions. Let's solve a 2D static equilibrium problem. A 10-meter beam weighing 500 newtons is supported by two cables. Cable A makes a 30-degree angle with the horizontal, and cable B makes a 45-degree angle with the horizontal. We need to find the tensions in both cables. First, we draw the free body diagram. The beam is horizontal with its weight force downward at the center. The two cables provide upward and sideways forces. I've color-coded the weight in red as an applied force, and the cable forces in green as reaction forces. Coordinate axes are shown for reference. Next, we resolve the cable forces into their x and y components. For cable A at 30 degrees, the x component points right and the y component points up. For cable B at 45 degrees, the x component points left and the y component points up. Now we apply the equilibrium conditions. The sum of forces in the x direction equals zero. Tension A times cosine 30 minus tension B times cosine 45 equals zero. The sum of forces in the y direction equals zero. Tension A times sine 30 plus tension B times sine 45 minus the weight of 500 newtons equals zero. For moments, we choose the pivot point at the left end, point A. This eliminates the unknown tension in cable A from the equation. The sum of moments equals zero. The weight creates a clockwise moment of 500 newtons times 5 meters, and cable B creates a counterclockwise moment of tension B times sine 45 times 10 meters. Solving the moment equation first gives us tension B equals 353.5 newtons. Substituting this into the Y-force equation gives us tension A equals 433.01 newtons. The final answer, rounded appropriately, is 433 newtons for cable A and 354 newtons for cable B. Let's solve a more complex static equilibrium problem. A 5-meter ladder with mass 10 kilograms leans against a wall at a 60-degree angle. The coefficient of static friction between the ladder and the ground is 0.3. We need to find the forces acting on the ladder. The free body diagram shows the ladder as a simple line. Forces include the weight downward at the center, normal force from the wall horizontally, normal force from the ground vertically, and friction force opposing potential sliding. Applied forces are shown in red, reaction forces in green. Friction plays a crucial role here. The coefficient of static friction mu equals 0.3. The maximum static friction force is mu times the normal force from the ground. Friction will adjust up to this maximum to prevent sliding while maintaining equilibrium. For equilibrium, we have three equations. Sum of forces in X, wall normal equals friction force. Sum of forces in Y, ground normal equals weight. Sum of torques about the base, weight times half length cosine theta equals wall normal times length sine theta. First, calculate weight. Mass 10 kilograms times gravity 9.8 meters per second, that equals 98 newtons. For theta 60 degrees, cosine is 0.5, sine is approximately 0.866. From torque equation, weight times half length times cosine theta gives 98 times 2.5 times 0.5 equals 24.5. Wall normal equals 24.5 divided by length times sine theta, approximately 5.66 newtons. Ground normal equals weight, 98 newtons. Friction force equals wall normal, 5.66 newtons. Maximum friction is 0.3 times 98 equals 29.4 newtons. Since 5.66 is less than 29.4, the ladder won't slip. The key decision here is that friction adjusts to whatever value is needed for equilibrium, as long as it doesn't exceed the maximum static friction force. Always start with a clear free body diagram. A free body diagram shows all the forces acting on the system, making it easier to identify what forces need to be considered in your equilibrium equations. Choose a convenient coordinate system. Align your axes with the problem's geometry to simplify force components and make calculations more straightforward. Be consistent with sign conventions for moments. Define clockwise and counterclockwise moments clearly, and stick to that convention throughout your calculations to avoid confusion. Carefully check your work. Verify that all forces sum to 0 and all moments sum to 0, and double-check your calculations in units. Consider simplifying the problem by choosing a pivot point that eliminates unknown forces from the moment equation. This reduces the number of unknowns and makes solving easier. Ensure units are consistent throughout the calculations. Convert all forces and distances to the same units to avoid dimensional errors in your equilibrium equations. Common mistakes in static equilibrium problems include forgetting to include all forces in the free body diagram, which can lead to incorrect equations. Incorrectly resolving forces into components can cause errors in the X and Y directions. Choosing the wrong pivot point for moment calculations will give incorrect torque values. Errors in algebraic manipulation, like solving equations incorrectly, are also common. Finally, not checking your final answer against the original problem can miss obvious errors. The key concepts of static equilibrium include the conditions that the sum of all forces equals 0 and the sum of all moments equals 0. Understanding both force and moment balance is crucial for solving static equilibrium problems, along with creating accurate free body diagrams. In conclusion, static equilibrium is essential for analyzing structures and objects at rest. Understanding both force and moment balance helps solve real-world engineering problems. Practice regularly to master free body diagrams and moment calculations. In the next video, we'll explore applications of static equilibrium in trusses and other structures.